what we're going to do today is we're going to talk about sorting today. It'll be lecture 11 if you're following along in the slides, if you've looked at those before. Because this class is still, it's just the second class and an introduction to programming. We're not going to go deep into sorting. In fact, some of the sort algorithms we won't even cover that are in those slides. But if you're interested and you want to look at those, be definitely some fun reading for those of you who are interested in learning more about these kinds of things. Okay, but we do want to cover some basic sorting algorithms. What we'll do is we'll cover two of them today. The two, if we're talking about the big O n squared algorithms, we'll talk about those two today, and then we'll talk about the two of the big O log n log n algorithms tomorrow. Okay, so let me go ahead and share slides here. Whoa. All right, yeah. All right, so sorting. All right, so what we're going to do is we are going to talk through and analyze a little bit and show some examples of insertion sort and bubble sort today. We will then talk about merge sort and quick sort tomorrow. And then there's this other stuff, this heap sort and bucket sort, some other, and a thing about an example about sorting large files and stuff. Useful for you if you want to take a look and have some more understanding of sorting in general, but a lot of this will be covered. We'll cover it kind of surface level, just kind of introductory level in this class, but then in your algorithms class, you'll learn more about these sorting algorithms. Okay, so why do we study sorting at all? Why would I even introduce this at all? One thing is that it talks about some creative approaches to problem solving, right? So again, these are just examples of how we can solve problems. And one thing that I've talked about multiple times, and one thing that I've said many times, is there's oftentimes not one correct solution to a problem. So if you were to ask me, how should I sort an array of objects? How should I sort an array of values, of integers, of strings, of whatever? There's lots of different ways that you could think of to sort it. If I had, for example, if we were still meeting in person and if I were to give you a quiz or an exam, what might be helpful for me would be to have when I go to enter your grades, would be to have all of your exams sorted in some way on the stack, or all of your quizzes sorted as a stack of papers, so that I could, as I enter them into my spreadsheet, it would be a lot easier for me to find your name or your student number. It would make it easier if I were to do that, if I were to have you on my spreadsheet sorted in a certain order, whether by student number or name, and then to sort the exams in the same order, and then I could just put them in very quickly, right? So it's helpful in practice, but the question would be, okay, so for the spreadsheet, it's easy. I click the drop down and I say sort, right? That's the easy sort, right? How it does it, we don't know, but it does it. But for me, what I have to do is I have to sort those exams. So how do I sort the 90, 100 exam or quiz papers into the order that I want? Well, I could search through all of the exams. I could search through all of the papers, and I could find the student whose name comes first, right? So probably somebody that starts with the letter A, right? I don't think there's an Abdullah in this class, but anyway, it would be maybe some students over there. So I would search through all the exams, find the student that starts with the letter A, and I would pull that student to the front. Then I would search through the rest of the exams, and I would find the next. It seems kind of long, right? It seems kind of long and tedious, but that's actually one of the simplest, even though it may run the longest, it's one of the simplest versions of a sorting algorithm that we're going to talk about today. Another way I might do it is I might say, okay, I'm going to take the first exam Okay, and I'm going to kind of put it to the side, and then I'm going to take the second paper, and I'm going to, if the name comes after the first, I'm going to put it behind, and if the name comes before the first, I'm going to put it in front of. Right now I have two papers that are in sorted order. Now I'm going to go to the third one, and wherever it goes, I'm going to insert it into where it goes. And then I'm going to take the fourth one, I'm going to insert it into wherever it goes. All right, that might be another option for how I could sort the papers. And that's another of our sorting algorithms we're going to talk about today. And these are just ways that we might do it in practice. And so I would imagine that if I gave 50 papers, 50 kinds of papers to each of you and said, I want, and randomized them up, shuffle them all up. And I said, I want you to sort these. I want you to put them in ascending order. I would imagine that each of you out there, some of you might do it the same way as someone else in the class, but I bet there would be quite a few different ways that you guys would do this, right? And that's the reason why we study this, is because there's lots of different solutions to our problems, okay? All right, so what kind of things can we sort? Anything that's comparable, right? So if two numbers are comparable to each other, which they are, we can sort those. Strings we can sort. Anything, again, anything that's comparable. So we could sort an array or an array list of geometric objects, right? If we made the geometric objects comparable, we can sort those. All right. Now, the types of data structures that we can sort need to be of the type of where order matters. All right. So like an array or an array list, we can sort. A linked list, we could sort. We would not be able to sort a set, right? Because a set is not an ordered thing, right? It's just thing that doesn't allow for duplicates. Right? So we couldn't sort a set, although there is a sorted set, which is a subclass, right? But which is a slightly different data structure, but a normal, just normal run-of-the-mill set, we could not sort. But the things that we can sort are things like array lists or linked lists. The main thing that we will look at in terms of sorting the data structure, we're going to look at an array. Okay, that's the things we're going to use so that we can understand, so we can see the data structure and how the sorting affects things and how it plays out. Okay, so the second example I gave, where I took the paper and I inserted it into my already sorted stack of papers, right? That's the first sorting algorithm we're going to look at, okay? And we call it insertion sort. And what happens is as we pass through the array, right, we get to a value and we say, okay, I am going to take this value, I'm gonna pull it to its side. Okay, so it's a part of a sorted array. So this array value here, 2, is sorted. Now I'm going to look at the next one, and I'm going to insert it into a 2-value array where these two values are in sorted order. So 9 comes after 2, so I'm going to put 9 after 2. So after I process this, after I process the second value, I have a 2-value sorted array. Okay. Now I'm going to go and process 5. Okay. When I process 5, I'm going to insert it into the array where it goes so that the values are in sorted order. So it comes after 2, but before 5. So what am I going to have to do? I'm going to have to move 9 to here, and I'm going to have to move 5 to here. Okay. Now when I go to process 4, where does 4 go? 4 goes after 2, but before 5, right? So what does that mean? That means that both 5 and 9 are going to have to move to the right 1 spot, and 4 is going to take over that second spot. Okay. Once I get to 8, well, it doesn't come after, it comes after 2, it comes after 4, it comes after 5, but it comes before 9. So I'm going to insert it into where the 9 spot and move 9 to the right. Now I get to 1. Well, there's a lot of movement here, isn't there? Because 1 is all the way back here at the beginning, which means that 2 and 4 and 5 and 8 and 9 all have to get moved to the right 1. Okay. Move this over. All have to get moved to the right by 1. And then 1 can take over that first spot. And then finally we process 6. And 6 goes after 5, but before 8. So 8 and 9 move over to the right. 6 gets put into that spot. Okay. One of the things that you'll notice about the insertion sort is that every time we process a position, at the end of that processing, we have a sorted array that consists of where the first n positions consist of a sorted array. Right? So notice that everything after that position remains unsorted, but everything up to that position is sorted. Right? So here, let's take a look at, like, for example, this step here. We have 2, 4, 5, 9 is a sorted array, but 8, 1, 6 is not sorted. It's part of the unsorted portion of our array. Okay, so we are building a sorted array up until once we're finally done here, right, we have a subarray of n positions, our entire array. It's all sorted, and the if you want to call it the unsorted part is the non-existent array at the end. So the whole thing is sorted. So like if we take one step back here, n is 7 values. So here at this point, before we process 6, we have a 6 value sorted array, 1, 2, 4, 5, 8, 9, and a 1 value unsorted array. Okay, if we think of it as 2 separate array sections, right? After we process 6 and we put it where it belongs, now we have a 7 value sorted array and a 0 value unsorted array. Okay. So then the question is, okay, well, how do we analyze this? How do we determine what the runtime is for this? Okay. Well, you might think, well, I process 2, then I process 9, then I process 5 and 4 and 8 and 1, 6. I process 1, 2, 3, 4, 5, 6, 7 values for a 7 value. Well, this is n, right? I only went through the array n times. The problem is that processing, looking at a value, we looked at each value one time, but processing the value did not take no time at all, right? The best example of how we look at this is how many things did we have to do to put 1 where it belongs? Okay. So in the best case scenario, 9 is already where it belongs for when we process 9. The best case scenario is 9's already where it belongs. We don't have to do anything. There's no work required to put 9 where it belongs. But the work required to put 1 where it belongs, way at the beginning of this array, this is the worst case scenario. And how many moves are required in order to put 1 where it belongs? We don't just get to put 1 in that first position and overwrite 2, because then we would lose 2. Right? What we have to do is we have to move 2 into this position. But before we can do that, we have to move 4 into this position. But before we can do that, we have to move 5 into this. But before we have to move 8 into this. And before we do that, 9 has to move into here. So what did we have to do for this 6 to make this 6 value array correct? We had to move 6 things, right? We had to move 9, we had to move 8, we had to move 5, we had to move 4, we had to move 2, we had to move 1. All right. So we had to do 6 moves in order to make this 1 insertion happen. All right. So yes, we looked at 1 that counted as one of our n look at the values, but we also had to do n moves as when n equals 6 here in order to make this happen. Okay, so that's the reason why insertion sort is what we would call a big O of n squared, algorithm. Okay, there's an animation if you want to look at this on the link here. You can see the animation there. Okay. All right. So again, this is the same thing where as we build, as we move through the array, right, we end up with a subarray that's sorted and a subarray that's not sorted. Okay. So this is the general idea for how the algorithm works. Right. To insert, so let's just take a look at this example, the 2594. We're processing 4. So first we need to save 4 to some temporary variable. Okay. Then we're going to take 9 and we're going to move it. Then we're going to take 5 and we're going to move it. Okay. Now we have an empty position and 4 needs to go there because it doesn't belong here, right? We don't need to move 2 because 4 is bigger than 2. So once we have that situation where we've moved everything bigger than the current value, right? And we've gotten to the next value down is smaller than the current value, we're going to put it into there. Okay, so then once we get to that situation, we've moved all bigger values and we have gotten to a smaller value, we're going to put 4 there. We're going to put that current element into that position. Okay. All right. So what we want to do is we want to pass through the list, right? And we want to insert, as we go through this, we want to insert list sub I into the sorted sublist that exists from 0 up to I minus 1. Okay. Now, you might say, wait a second, don't we need to start with I equals 0? Why are we starting with I equals 1? Well, what's the point? What are we trying to do? We're trying to get, again, a subarray of sorted items and a subarray of unsorted items, right? A subarray here where the values are sorted. At the end of processing this, we're going to push this into here. We're going to have now a subarray of sorted, right? So 259, we process 4. We're going to push it into here. 2459 is now our sorted subarray. And our array after the value that we're processing is still unsorted, right? So then the question is, what I posed was, why don't we start with I at 0? Well, if all we have is one value, right? I of 0 would just be a one value array, right? It's already sorted. An array of only one value is already sorted. We don't have to do any work to sort that, right? Okay, so that's why we start with 1, is because we look at a single value subarray, a subarray of only one value, and we say, well, that's already sorted. We don't have to do anything to that, right? And so at the end of each time through the loop, right, our subarray from 0, from the first position up to whatever I is going to be a now sorted array. Okay, and then once we complete going through our list.length, our n items, then list of 0 up to n minus 1 is sorted, so the whole thing is sorted. Okay, so then the question is, for the insertion sort, is how do we do this part, right? Because this part, that's Java, right? This is an easy loop, right? For I equals 1 up to n minus 1, make n minus 1 a sorted sublist, all right? So the question is, how do we do that? Okay. So let's expand this out. So the idea is every time through, we're going to save the current value we're looking at. So we saved back here, the example was we save 4 to a temporary variable. All right. Now we're going to go down from the end of our current sorted list. So our current sorted list is what? It starts with I minus 1, right? And we're going to go from I minus 1 down to possibly 0, but it's either we get through the whole list or, right, so either as long as k is greater than or equal to 0 and the value we're looking at is greater than the current element, right? Then we're going to keep going down. And what we're going to do is we're going to copy. So if we look at our previous example, 2, 5, 9, 4. Okay. I is 3. Okay. So, okay, we started list of 2. Is list of 2, 9, greater than the current element, 4? Yes. So we copy into k plus 1, 3, the value at k, 2. So 9 gets copied over. Then we check, is 5 greater than 4? Yes. So now we copy 5 into a position ahead of where it was. Then we go down. Is 2 greater than 4? No, it's not. So we hop out. What was 2? 2 was at list at 0. So now the list at 0 plus 1. The list at 1 is equal to the value 4. Okay. So this is how we would do this. This is how we would insert into that as we keep, every time we look through, right? We look through our values until we get to one of two situations. Either the current value in the list that we're parsing back through from the end, if either it's less than or equal to the value we're looking at, or the other way that this loop could end is if k becomes negative. If we look at the first value, so for example, the example that where that happened was we processed 1, right? So we said, is 9 greater than 1? Yes, move 9. Is 8 greater than 1? Yes, move 8. I think it was 8, right? Yep. Okay. Is, what is it? 5 greater than 1? Yes, move 5. Is 4 greater than 1? Yes, move 4. Is 2 greater than 1? And that's where list at 0 was 2. List at 0 was 2. 2 is greater than 1. Yes, move 2. Now k becomes what? K becomes minus 1. So now this is no longer true. So we pop out of the loop and we say the list at 1 is equal to our value. So we insert it into the very beginning of the list. So the two possibilities of how this loop ends are we find a value that's less than or equal to our current element. The other possibility is k becomes negative. We exhausted, we looked through all the rest of the array and found nothing. Okay. All right, so that is insertion sort. Okay. We'll look at that in a visible format in just a moment. Okay. But the other n-squared sorting algorithm we want to look at is what's called bubble sort. Now, there's not as many slides on this, unfortunately. But the idea to solution thing is still kind of the same idea. It's how we're going to come up with the code for it. Okay. Now, bubble sort, what its idea is that the greatest value, so it's kind of a sorts greatest down to least, right? So the idea is it's going to bubble up the greatest value into the last position. And then it's going to do that for the next n-1 items. Then it's going to do the next for the n-2 items, n-3, up until we exhaust the list. Okay. Notice this is the same example as before. I think it's, well, it's a subarray. There's no 6. The last value 6 isn't there. Okay. But what we do is we look at the first two values. Okay. Is 2 greater than 9? Yes. So it stays where it is. So now, at this point, right, we have the thing that's less than the other thing here, and the thing that's greater than the other thing here. All right. So now we look at the next two values. Is 9 greater than 5? Yes. So we swap them. If we end up in a situation where they are out of order, we swap them. right? So what happens? 9 moves up, 5 moves down. Is 9 greater than 4? Yes, so we swap them. Is 9 greater than 8? Yes, so we swap them. Is 9 greater than 1? Yes, so we swap them. Now that's the first pass. Now we don't have to look to the end of the array again, do we? We only have to look through, for this next part, we only have to look through the first 5 items. But again, we do the same thing. Is 2 greater than 5? No, we leave them. Is 5 greater than 4? Yes, we swap them. Is 5 greater than 8? No, we leave them. Is 8 greater than 1? Yes, we swap them. Do it again. Is 2 greater than 4? No, we leave them. Is 4 greater than 5? No, we leave them. Is 5 greater than 1? Yes, we swap them. Is 2 greater than 4? No, we leave them. Is 4 greater than 1? Yes, we swap them. And then finally, is 2 greater than 1? Yes, we swap them. Okay. So the way that this works, the way that it looks, is the greatest value in the list bubbles up through, swapping with values along the way until at the end of the first pass, we have an unsorted n-1 array, and we have a sorted on the end n array. Okay. There are situations where bubble sort is better than insertion sort. There are situations where insertion sort is better than bubble sort. Both of them have a time complexity of n squared. And again, the reason why is because in the worst case scenario, how many swaps would have to be made? Well, we're going to look at that because in the example, both of them, both insertion sort and bubble sort, the worst case scenario is you want to get an array that's sorted in ascending order, meaning lowest value to highest. And in both cases, the worst case scenario is you have an array that's already sorted but opposite. An array that's already sorted but highest to lowest instead of lowest to highest. Okay. Just like with insertion sort, there is an animation available if you want to look at them on here. Okay. So let me pull up the let me put up the examples here. We'll take a look at that. Hold on just a second. Let's see. Let me share the examples. Make sure. All right. All right. So here's our insertion sort. Okay, notice it's the same thing as in the slides, where what we do is we pass through the list, and for each time through the list, we're going to end up with a 0 to I sorted array. Okay. Bubble sort. All right. Okay, so that's an example that's inside of the bubble sort. Maybe I should add that to the insertion sort for you guys, right? But the bubble sort, all right, we're going to, every time through, right, we're going to make sure that the highest value that we've encountered so far bubbles its way through the bubbles its way up through to the end of the array. Okay. All right. Basically, if you see this need next pass, right, is that if the array is already sorted, if we never made any swaps, if we looked through the array one time all the way through, right, and we never found a swap, we never had to swap, not one time, then what's going to happen? We don't need to pass through again, right? We already looked through the array and we saw that it was sorted already. We don't need to pass through it again, right? Okay. I hope you understand why that's there. One thing I can tell you that in the traditional bubble sort, we don't do this. This is just not even a this is not a thing, right? We don't use that need next pass because the traditional bubble sort doesn't look ahead like that. Okay. So what this need next pass is there for is to help make an n squared algorithm run just a little bit faster. Okay. So what we'll do is we'll look at an example here. All right. We'll look at a few examples. Let's do this. Okay. So if you see, I have let me make it only 5 values to make it a little bit easier. Okay. All right. And then, you know what, I'm going to do one other thing too. An already sorted array and an already sorted array. So you can see how this works too. First, no. So what we're going to do is we're going to look at how the sorting algorithm works inside. So I'll run this whole canvas thing, which you guys know I like to use. All right, so we create this array, ID array insertion sort. We're going to step into the insertion sort, and I want to look at what the list looks like. So you see this is, all right, this is the 5, 4, 3, 2, 1. Okay. Now remember the way that insertion sort is. It's going to look at the first value, or sorry, it's going to say the first value is already sorted. So it's going to look at the second value and it's going to insert it where it belongs. Okay. So the first value is what? It's 4. All right, so let's go ahead. It's the 4.0. All right. So now we're going to move 5 to here. And then we're done. We've exhausted the list. We're going to put 4 into that first position. Right? Okay. Now 3. We're going to see that 3 is less than 5, so we're going to move 5 over. We're going to see that 3 is less than 4, so we're going to move 4 over. And we're going to put 3 where it belongs. Notice this is now a sorted array and a non-sorted array. 2. We're going to move 5. We're going to move 4. We're going to move 3. And we're going to put 2. Okay. Finally, we look at 1. Move 5. We're going to move 4. We're going to move 3. We're going to move 2. We exhausted the list. We're going to move 1. We've reached the end of our list. And now we're going to display the values in sorted order. Okay, so you see how that works. Now let's take a look at the bubble sort one. Okay. All right. Okay. We're going to look at this, and we're going to say, all right, need next pass right now. It's false because we haven't made any swaps yet. Okay. Is list sub I, what is I? I is 0. Is the list at I greater than the list at I plus 1? Is 5 greater than 4? Yeah, so we're going to swap them. All right, so we swap them out. And we do need a next pass. So now we're going to look at, is 5 greater than 3? Yep. So we're going to swap them. Right. Now is 5 greater than 2? Yep. We're going to swap them. Is 5 greater than 1? Yes, we're going to swap them. So notice that we bubbled up 5 to this position over here. Right. And then we're going to do the same thing with 4, where 4 is going to move into that final position, into that final subarray position. All right. So then 3 is going to move into this final position here. And then finally, we swap 2 and 1. Okay. And you guys might remember this. I hope you guys remember this over here, the swapping algorithm. And so what they did here is we put the swapping algorithm, put the swapping code inside of the loop here. You could have also written a method for this. You guys remember that we had the whole swap method discussion last semester about how to do that and why sometimes for a method, you know, if it was just variables, we couldn't do that. But with an array, if we give it an index of the first item and an index of the second item that we want to swap, that we can do that with an array. Okay. All right. So then we're done. And then we display our sorted array there. Okay. Now the reason why I wanted to do this here, why I wanted to do what if they are already in sorted order? Okay. The insertion sort, because we look at each value and we insert it where it belongs, we don't pass through the array, right? We don't pass through the whole array until the very end, until we're looking at the last value in the array. But with the bubble sort, because we are bubbling up the value, right, to where it belongs in the array, we pass through the array. So if in the course of passing through the array, if while passing through the array, we discover that the array is already sorted, the bubbling array that we're looking at is already sorted, well, we don't have to do any more work, right? This would be like if I was trying to, again, order your quiz or exam papers, and I was looking through them and I realized, oh, hey, this section of 3 or 4 exam papers are already sorted. I don't need to do anything with those. I don't need to move any of these around. It's already there. Okay, it's already sorted. So let's see how this works. All right, as we step into these. Okay. All right, so we're going to look at 2. Right? No need to do anything. We don't need to move anything along, do we? Right? So we're going to go through and do nothing each time. It's already sorted. Okay, a lot faster, right? So this is because this is a best case scenario. Our best case situation is the array is already sorted. All right, so we're done with that. Okay, what about this one? Bubble sort. So watch what's going to happen. Same thing though. We're going to pass through and okay, we're going to check, is the value at 1 at index 1 greater than the value at index 0? Yes. So we're not going to swap anything. 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 Okay. We didn't make any swaps. So what's need next pass? It's still false. This condition, right? It is, right? So even though K is less than the list length, right? Even though K is less than the length of the list, and that is still true, this other part is false. We already figured out that this is already sorted. Okay, so we're done. Okay, so that helps bubble sort run a little bit more quickly, is what the purpose of that need next pass variable is all about. Okay. So that was an introduction to the n-squared algorithms for sorting. Like I said, let me get rid of that. Like I said, tomorrow we'll talk about the n log n algorithms, merge sort and quick sort, as its name implies it's a fast sorting algorithm, quick sorting algorithm. All right, but I just wanted to introduce you guys to some general sorting algorithms, some of the simpler ones. What you will notice, turn my camera back on. What you'll notice as we do this is that the algorithms that are slower in runtime are generally easier to understand the code. There's not a lot of complex coding involved. But the algorithms that are faster in runtime usually require us to do some more complex coding. Another example that from last week that we talked about with that was that whole method that we wrote to add up the numbers from 1 to n, or add up the numbers from what was it? From like some A to B, right? That if I did that as a loop or as a recursive algorithm, it was easier to understand just looking at the code, what the code was doing, but it wasn't very fast, right? It was a big O of n algorithm. However, if I did it as a single line of code that calculated the n squared plus n over 2, all right, just a single line of code, much faster, big O of 1, right? But just looking at it immediately, you weren't sure that that's what that was doing. You just knew that it was calculating some mathematical function, right? And so what we had to do is we had to add a little comment in there and say, this is what this method is supposed to be doing, okay? So like I said, generally faster algorithms are going to be a little bit more complex coding wise and may need some explanation in comments about what's going on. But simpler to code sometimes means that we sacrifice runtime, makes it a little bit slower to run. Okay. Again, neither is bad or good. It's just a matter of which one is enough. All right, which one is good enough. For example, when we're thinking about traveling. So an example I've often used with you guys is traveling from Antalya to Ankara. Many of you know that I used to live there. Yeah, there's lots of different ways to travel from Antalya to Ankara. All right, we can go by plane, we can go by bus, we could walk, we can drive our own car if you have a car, right? I guess right now you can't go to Ankara, but yeah, you know, at least we can travel from Antalya to other places for those of us who are not who are not in some of those other lockdown cities. But the thing is each of those, there's a trade-off, right? The generally less expensive options to travel from here to Ankara also come with them more time. It takes longer to get there, right? And so the question is it worth it? Is it worth the extra money to get there faster? Well, for some people it will be, and for other people it won't be, right? So in the same way with sorting algorithms, with any algorithm, is the extra time that it takes to run the algorithm worth the cheaper cost of developing the algorithm? And the only people that can answer that question are going to be you and the people you're working with, and probably your customer, your user, and your manager as well, to determine those things. Okay. All right. So that was an introduction again to the big O n squared algorithms. Tomorrow we will look at the n log n, and unless there's any questions, then I will see you tomorrow morning, same time. All right. Have a good afternoon and stay healthy. Salud Cullen.